Hi, in this lecture, let's work out the derivation of the wave equation for waves propagating down the length of a string. So if I have a piece of string like this one here shown vertically, or the one on this slide shown horizontally, and we pluck it, it will lead to string waves that travel down the length of the string. In this case, hard to see because they propagate up and down and reflect very quickly. But if I pluck it, there's some motion up and down the string, and that's what we want to work out. So we're going to start out with some plucking here, say at this certain point in the string. That'll lead to a phenomenon where that pulse will propagate down the string, and we want to understand what governs the propagation of that pulse. What form of solution do we get for a plucked string? Now, what do we mean by a string? We really mean a string under tension, so it's held fixed, say, at two ends, and there's a certain tension or force along the length of that string or rope or whatever it is. And it has to have some mass, so we'll give it a linear mass density. That's the mass per unit length. We'll abbreviate that by Greek letter mu, and SI units is measured in kilograms per meter. And that's just the mass per unit length, so that'll come into play just as the tension in the string, which is a force measured in newtons. So here's that same diagram shown here on the left side of the slide. We're going to discuss the motion of an element of that string, and it should be obvious, but let me just say it. We're plucking it transversely, so the wave will propagate down the length of the string. That'll be in the horizontal direction, which I'm going to label as the x direction. But we'll pluck it in the vertical direction, which I'll call the y direction. And that's the displacement that will propagate down the string. It's a transverse displacement. String waves are transverse, meaning the displacement is perpendicular to the direction of motion. If it's moving in the x direction, the displacement's in the y direction. This is in contrast to, say, longitudinal waves, which are in the same direction. Okay, but one other thing we're going to assume is we're going to assume that the angles theta 1 and theta 2 are small. What does that mean? Here's an element of that string that's been plucked, if you like. It's at some angle now in the xy plane. We can measure the angle, say on the right side, the angle above the horizontal direction, and on the left below the horizontal direction, respectively theta 2 on the right, theta 1 on the left. But we'll let those angles be very small, and you'll see why. We'll do a small angle approximation. And then the length of the string is between x1 and x2 on the x-axis. But we'll let x2 be rather close to x1, infinitesimally close, so x2 will just be x1 plus dx when we do this calculation. Okay, so that's the setup. We're going to pluck this, and we're going to see how we can get an equation to describe the propagation. If we take a small element of the string that's been plucked, again from x1 to x2, which was really a length of only dx, the mass of that string element dm is the length dx, and let me call it dl generally because it's at an angle, but if we let those angles theta 1 and theta 2 be small, that's going to be approximately equal to dx, the extent along the x-axis. So that length times the linear mass density, how many kilograms per unit length, gives me the mass element dm. So my small element of string has mass dm, and we can apply Newton's second law to see how this governs the motion. So Newton's second law, F equals ma, of course, tells you that there's an acceleration when there's a force applied to a mass. In this case, we have the force that's in the string. The mass of the string element is dm. It's an infinitesimal mass, and the acceleration is a in the y direction. Again, transverse waves, so that's in the y direction on my graph. But acceleration is just two time derivatives of position. So that's d squared y dt squared as a second order derivative. And the mass, as we just argued, was mu times the length of the string, which is approximately mu times dx if the string is nearly horizontal where those angles are small. So that's the MA part of Newton's second law. What about the forces? What goes on the left side of this equation? The net force acting on this element of string, which will govern whether it's going up or down. That has to do with the tensions on each side of the string. So a string, as you know, has a certain tension. It pulls, if I pull one force, a certain amount on one side of the string, that's a certain tension in the string, but it's in the other side I have to pull in the opposite direction the same amount. So on each end of the string I have the same tension, one going to the right, one going to the left, depending whether you're in the larger x side or the smaller x side. And those tensions have to balance. If they did not, there would be a net force and the string would have a net acceleration. But if a string is held fixed, it's only having transverse displacements, those forces essentially balance. So they have the same magnitude. So the F1 on the left and the F2 on the right, those have to be approximately equal to, or have to equal the tension in the string. That's going to balance. They don't necessarily have to exactly balance in the x or y direction. I'm just saying the net tension does have to balance. Otherwise the string starts moving. Okay, now we can talk about the x and y components though. So let's talk first about the component of F1, that's the left side, and component of F2 along the horizontal direction or the x direction, and I'll just make that clear. This is x along the horizontal direction. So F1x, so the tension, the way it works in a string is it's pulling on both ends, right? So on the left side it's pulling to the negative x direction. And what is the amount? Well, that would be the tension in the string minus t. That's this arrow here, the magnitude is tension t. If I took the cosine of that angle theta 1, the dip angle below horizontal, that's the projection along the x-axis. So I'm trying to work out the direction along that axis. So that's t cos theta 1. Likewise for F2, I want the projection onto the x-axis. I want this component, so that'll be t cosine theta 2. But if theta 1 and theta 2 are small, I'm going to apply what's called the small angle approximation. And that means for very small angles, the cosine of a small number is approximately equal to 1. So minus t cos theta 1, the minus, by the way, is because the force and tension are pointing in the negative x direction. That's going to be approximately equal to minus t. And F2 times cos theta 2 is approximately equal to t as well, because it's t cos theta 2, cosine of a small angle is about 1. So they essentially approximately balance in tension in the x direction. What about the y direction? Well, now I've got to work out the transverse components. So I have F1, so that would be kind of down on the left side, and F2 has a vertical component up into the on the right side. So they're very similar. On the left side, the tension is pulling in the negative y direction, so I've got a negative sign there. But instead of cosine, I replace that with sine. That gives me the opposite leg of this triangle, where theta 1 is the angle below the horizontal. So minus t sine theta 1 is F1y, but in the small angle approximation, where theta 1 is small, sine of theta 1 is going to be approximately equal to the tangent of theta 1. Because what is tangent? Tangent is sine of theta over cosine theta. But we just argued cosine theta is about 1, right? So sine of theta over cosine theta becomes sine theta over 1. So yeah, that's approximately true, right? But what is tangent of theta? Tangent of theta, here's my theta 1 again, down over here on the left side. That tangent is the opposite side of a triangle over the adjacent side. Well, the opposite side is this vertical amount in the y direction, and the horizontal side is the x amount. And so the tangent is nothing more than the derivative here, dy dx. This looks like dy in the vertical direction and dx in the horizontal direction. Not necessarily the same dx I'm talking about here, but just as in terms of a derivative. So my force on the left side, force 1 in the y direction, minus t sine theta 1, because again it's in the negative direction, but that's approximately equal to minus t tan theta 1. Again, it's pointing in the negative direction for the tension. But that's minus t times the slope, this derivative dy dx. You see that? And dy dx is the derivative of this shape, whatever shape this traveling string wave will have, but it's going to be evaluated at position x1, the left side of the element of string. So it's the slope dy dx evaluated at x1 times the tension, and then with a negative sign because it's pulling down in the y direction. So that's F1 in the y direction. What about the right side? Well, that's tension sine theta 2 to get the vertical component in green shown there. But again, just they argue with the small angle approximation, sine theta is approximately equal to tan theta, so it's t tan theta 2. Again, now it's plus, not minus, because it's tension pulling up in the plus y direction. So it's tension times the slope, dy dx, that derivative, evaluated now at x2, which is x1 plus dx. So I have the vertical tensions on the left and right side, position 1 and position 2, and they're related to the slope or derivative of my string element at those particular locations. So what is the net force? Well, I had a positive amount pulling up on the right side and a negative amount pulling on the left side, so there's obviously going to be some difference that may or may not balance. So I'm adding those two forces, F1 in the y direction plus F2 in the y direction. And F1, that's going to be negative, so I put it here on the right for the moment, minus t dy dx evaluated at x1. F2 of y was positive, as we just worked out, that was t dy dx evaluated at x2. So it's this difference. Tension times the slope at position x2 minus tension times the slope at position x1. So that's now the left side, just to remind you of Newton's second law, F equals ma, shown up here at the top. And what was the ma part? That was, the mass was mu dx, and a is just d squared y dt squared. So this is the right side. So that's what we've come to. We're just applying the forces involved, the tensions in this string, assuming some arbitrary displacement and some slope, and this is how that would have to work out to balance. But let's look at what we've done here when we take these infinitesimal lengths. When position x2 is just dx away from position x1, that's where we value them. But if we let that go down to 0, so if we take the limit of dx goes to 0, and if you like, I can take the dx on the right side of the equation above and divide by both sides of the equation above. Right, so that'll cancel it on the right side, but not on the left side. So I have the 1 over dx here, and then I have the difference in derivatives, and so that's what I've shown here. The difference in derivatives at the two locations, divide by dx. There was a tension here, which I'm going to divide out also on the left side, but I have to divide it also on the right side. So I've done that. And so I have just this thing with this limit of 1 over dx times the difference in derivatives equals now the mass density mu over the tension, because I divided the tension. Dx I already divided out on the right side, so it's equal to times d squared y dt squared. That's this right side. A little bit messy, but there you go. But it's this left part I want to discuss. This is the difference in derivatives evaluated. This is like two functions. A function dy dx at x1 plus dx minus the same function dy dx evaluated at x1. That's over dx is the definition of a derivative. The function at x plus dx minus the function of x over dx. So this is a derivative of this function, but the function itself is a derivative, dy dx. So this is two derivatives of the position y with respect to x. That's what we're showing here when we let dx go to 0. And the right side of the equation had the mass density mu. It had that second order derivative in y with time for the acceleration, mu d squared y dt squared, and I divided the tension from the left side to divide on the right side. And so what I'm left with is this equation in the bottom right here. The two derivatives in y with respect to x squared, that's what this left definition basically is, equals mu over tension, the mass density over the tension, two derivatives of y with respect to t squared. Now I've used the curly derivative symbols, the partial derivative symbols, because now y is a function of both the position x and of time. So what a partial derivative means is, if I take the partial derivative with respect to x, is I hold time fixed and I take a derivative only with x treated as the variable. The right side is I take two derivatives with respect to time, where time is my variable, but I hold x as a constant. That's what those mean. So that's the equation that's important to have worked out right there. as I'll show on the next slide, this is an equation for traveling waves. So I've cleared off the work there. I've kept the definitions here for tension and linear mass density. And as I just said, d squared y dx squared equals mu over t d squared y dt squared is a wave equation. It can have the general form where I've replaced mu over t as 1 over v squared. Now for that to be true, v has to be the square root of t over mu, the tension over the mass density. And so if I squared that, I have t over mu, and then I take 1 over it, and that gives you mu over t like the equation had. So that's true, but this is a general form of traveling waves in one dimension in x. So that's basically the characteristic form of any traveling wave phenomenon, at least for one-dimensional ones. Now, we can work out, in fact, and see that even though I called this v, how do I know it's a speed? Just look from dimensional analysis. Tension is a force, right? So that's newtons. And mass density is mass per unit length. That's kilograms per meter. Now, what is a newton? Well, I could use, for example, F equals ma to figure out the units, if you like the dimensions. Force is measured in newtons. It equals ma, which is mass times acceleration. So kilogram meters per second squared is what a newton is. And divide by kilograms per meter. So I see that the kilogram cancels here, and I have meter per second squared over meter. Over inverse meters. That's going to become meter squared over x squared. This will be meter squared over x squared. S squared. Take square root, just gives me meters per second. So dimensionally, it works out, right? So t over mu, take the square root, gives me something in units of speed. But how do I know what the solution to that partial differential equation is? It's partial differential because it's got partial derivatives. So that's where PD comes from. How do I know what the solutions are? Well, I'm just going to propose what the solution is, and you can plug it in and show that in fact it solves the equation. Solutions to such an equation are sinusoidal in nature. It'll have some, so my function y of xt here has some amplitude, which I'll call ym, the maximum value of y. And I claim there's a sinusoidal function that comes for this dependence. And the arguments of that function are kx plus or minus omega t plus phi. Well, before I mention that, so let me just argue what this means. Phi is the phase constant. It could be 0. Just let you set up an arbitrary phase for my traveling wave. K is the angular wave number. And omega is the angular frequency. So it's kx plus or minus omega t. The plus or minus tells you which direction the wave is moving, whether to the left in the minus x direction for plus, or to the right with the minus sign in the plus x direction. You can see that this will solve this equation because if you take a derivative of a sine function, whether with respect to x or time, the derivative of sine will be cosine, right? But then you take two derivatives, and you take a derivative of cosine again, and you get back to, in this case, negative sine. So you're going to come back to a sine function for both of them, because they're both two derivatives of this function. Now there's the chain rule to take into account. So each time you take a derivative of this function, you're going to pull out either a k or an omega, whether you're taking derivative with respect to x, like on the left side of the differential equation, or with respect to time for the right side. So that can only be true, though, if we have a certain relationship, which I'll explain in a moment. What I was just going to point out is, again, the plus or minus either is allowed, depends on the direction the wave is set up to move. And if you happen to like to work with complex numbers, we can represent this function here as in complex notation, a complex exponential, and you just take the real part of it when you want a physical answer. Literally speaking, this would be the cosine, but again, if you had a phase angle of 90 degrees, you can turn it into a sine. But as I said, I've argued that it has to be a sinusoidal function like sine or cosine, but it only works if I plug in, because of those chain rules, if when I take two derivatives in x, the chain rule will pull out k once and then twice, I'll have k squared. On the right side, I take two derivatives. Oh, sorry, I'll look over here. Two derivatives with respect to time. So pull out omega once and then twice will be omega squared. There was a 1 over v squared. So it's only true if that's satisfied, which put another way means the speed equals the ratio of the angular frequency over the angular wave number. V is omega over k when I take the square root of that equation. So provided that's true, this is the general function that solves this wave equation, which is solving for string waves propagating down a string in one dimension with a certain tension and a certain mass density. And as I said, V of omega over k is that key ingredient there. All right, so that's the math part of it, okay? So basically we showed by just using f equals ma and then taking the infinitesimal limit, we worked out some derivative definitions and we got this wave equation. Aside from the math, how can we also kind of qualitatively understand this equation shown here in the box above at the top? So let me discuss that for one moment before ending. So what is the physical interpretation of the string wave equation? It's actually quite geometrical in a way. So here's the wave equation again on the left now. I've got two derivatives in y, the displacement in y of the string with respect to x, equals 1 over v squared, two derivatives in y with respect to t. In other words, the acceleration, right? The left side, so that's the change in the slope of the curve. So it's the two derivatives is the slope of the slope, if you like. So imagine I have a wave, part of that sinusoidal function. It looks like this blue curve in the middle diagram. All right, so it's kind of reaching near a peak. There's a tension pulling down on the left and tension pulling down on the right. So for that curve, the slope, okay, it's positive on the left, dy dx is positive, then it's negative on the right. But the second derivative of that is negative. The slope is decreasing. It was positive, 0, and became negative. So the second derivative is negative here in that case. All right. So in this case, d squared y dx squared is less than 0. It's negative. But that tells us that the right side has to be negative, which means the acceleration has to be negative. That's telling me acceleration is in the negative y direction, which would be down in this diagram. So when the string has a shape like that, the string wants to accelerate back downward, because it's not going to keep accelerating up and just keep going up. It's going to reach a limit and want to come down. So when it's come like this, the acceleration is in the downward direction. If the string is bowed in the opposite sense, like here shown on the right, in this case, the slope was negative on the left, became 0, and became positive on the right. So that means the second derivative, the slope of the slope, d squared y dx, I should have put an x squared before, sorry about that. In this case, it's positive because it's always increasing the derivative or increasing the slope. So in that case, that curvature is positive, which means the right side of my equation is positive, which means the acceleration is in the plus y direction, which is up. So when the string's down here, it now wants to accelerate back up, and that's what gives you the oscillation up and down for that string wave. So that's kind of what this wave equation is telling us for strings in a qualitative sense. Okay, that ends this lecture on the derivation of the wave equation for traveling string waves, which are transverse waves, just to remember.